one final demo of why or in one way in which PCA can be used. I'm showing you here an interesting data set. It's from Markus Stöckli. He's one of the pioneers of imaging mass spectrometry. He's now working for a big chemical company in Basel. And imaging mass spectrometry means that you have a sample and a laser beam that hits the sample at one point after the other to ionize it, and you then have a mass or a mass analyzer that will give you for each point a complete mass spectrum. So you now have for each point in this image a full spectrum of, depending on the instrument and the settings, a few hundred or a few thousand channels. Now these few hundred or few thousand have here been summarized in just 100 channels that I'm clicking through here. In particular, here only the most dominant peaks from the mass spectrum were used. And do you recognize what this is? Some sort of, yeah, a dead animal, right? In fact, this is a deep frozen mouse cut along its axis. It sounds sadistic, but it's actually for a purpose. Namely, these people want to study where drugs distribute in the body and how quickly they distribute, and in which organs they have the highest concentration. This is important for all kinds of drugs, but in particular for cancer treatment, to see where the stuff goes. Okay, so what you see here is this animal which has been frozen, cut in half, and now you see for 100 different masses the distribution of this particular of compounds with that mass across the animal, but you also see very strong preparation effects here. So you see these 4 plates which are artifacts from the measurement. Ideally, they would not be there. Ideally, you would have a nice image. You also see that it's quite noisy and so on. Now there is certainly a lot of information in these 100 channels, but as a human, it's difficult to look at that sort of data. So we're used to color channels, and we have, in our eyes, we have receptors, color selective receptors for red, green, and blue, but we don't have 100 different color selective receptors, which is why it's difficult for us to look at such multispectral data. So it would now be nice to somehow summarize all of this information in fewer pictures, and one possible picture would be a score plot, which is something that I've not done here. So in this score plot, each pixel would be one point in this scatter plot, and I could then see if there are interesting clouds of pixels, so interesting pixels or interesting groups that somehow behave similarly. Or I can look at the principal components, and I have computed them here, and for this data set here it took a few seconds, and I can now color code these principal components and the principal components and look at them one by one. So this is the first principal component, which I've color coded in red, and then there's the second principal component in blue, and the third principal component in green, and then I can switch them all on together, and then you see this compound image. So now these 100 dimensions have been compressed into just 3, and these 3 have been used as the red, green, and blue channels in this image. And then you see some features like the spine here, or the brain, and some intestinal organs there. You see it doesn't do wonders. So the original data was quite noisy. This still is noisy, as you can tell. But it's one way of summarizing the information in the image. Now PCA for that kind of data is not the best method, because the original data is all positive. So you have ion counts which cannot be negative, and these principal components here, they will have positive and negative values, and then the coefficients in the spaces will also be positive and negative, which is a little bit unnatural for count data. And there are different methods that we won't have time to talk about today, like partial, or sorry, not partial, but probabilistic latent semantic analysis, which are more appropriate for this kind of data. Okay, actually last year I did talk about just that, probabilistic latent semantic analysis in some detail, but for this year I prefer to spend the time on giving you a general overview of these bilinear decompositions, because the PCA that we've looked at is just one example of a bilinear decomposition. So I'm calling this big picture bilinear decompositions. And their role in unsupervised learning. Now I'm starting with a very high level introduction. As a general reminder, in supervised learning we have, for example, a vector of labels, which could be y, and let's say we just have a single label for each of n observations, and we have our matrix collecting the features, matrix X, where I have p features or p measurements for each of the n observations. And if I now want to perform linear regression, for example, so the aim in supervised learning is to make valid predictions, so predict correct y's given the x's. And in regression, I would, for instance, say that y equals b transpose x. And if I want to complete the picture here, I would draw my matrix beta, or my vector beta, which is dimensionality 1 by p. Then I would have y, beta, and x. Okay, but generally speaking, we want to go from x to y. And all of the regression, all of the classification methods and so on that we study are doing just that. And this regression is just a particular example of how to do that. Question? No? Okay. Now, in unsupervised learning, we only have this x for us. So unsupervised learning given x only, we want to do things like reduce the dimensionality, which can serve different purposes. One aim could be to summarize the data. Like in the last demo that or the last data that I showed you, I just wanted to summarize my data. Or in a different field, the same thing is called compression. I want to express my data in fewer numbers. So sometimes I just want to store space on my hard disk drive, or on my, I want to save bandwidth in my network. In other cases, I really want to improve the interpretability of the raw data, simply because the raw data would be too many numbers to look at. Or I may want to cluster. That is, find natural groupings in the data. Or I may want to visualize it. And talking about PCA, we've seen two ways of visualizing today. In this satellite example, it was the score plot that was more interesting or more relevant to me. And in this mass spectrometric imaging plot, it was the loadings or the principal components themselves that were of more interest. Not true. Not true, because can you go back, please? Because what I showed here were also the values in terms of the principal components. So it was the scores that I color coded here, and I said something different because it well, because the writing there misguided me. So it's not my fault at all. Huh? It's the scores that were plotted here and color coded into the red, green, and blue channels. Okay. So those are the aims that I have in unsupervised learning. And it turns out that much of these aims can be achieved by means of bilinear decompositions. They are an important means to achieve the above goals. Okay, why is it called bilinear? Simply because I express x as a factor of something with something else. Now, in general, or if I don't give any other constraints or additional information, this problem is ill-posed, because I could, for instance, write 12, I'm just using a scalar example now instead of the matrices, but I could write 12 as being 6 times 2, or I could write this as 3 times 4, and so on. So this is ill-posed in general. So to come to a unique method, we need additional assumptions or additional constraints, additional prior knowledge. So for example, I could make a restriction on the rank of these matrices, or I could request sparsity or something like that. So why have I chosen these letters? I have assumed that x would again be p by n, p features and n observations. B would be p by r, and c would be r by n. And I've written c for coefficients, and I've written b for bases, without specifying that it should be orthogonal. And for example, if I now require r to be small, then I express or I approximate my original observations in terms of few basis vectors only, which I hope you would agree is a simplification of the original problem. Or is that gives me something that makes arguing easier. Let's say if I restrict this rank to be 3, then I can describe a single observation with only 3 numbers, rather than, let's say, the 100 numbers that correspond to the 100 measurements or the 100 features that I had for each observation. And if I'm just using 3 numbers instead, I can visualize it in 3D. It's much easier to analyze. that kind of data. Now, we have a big divide, a big watershed, according to whether this basis B is pre-specified or if I learn it from data itself. So we have two important cases. The basis B can either be data independent, so it means people typically here use bases with nice mathematical properties, or it can be data dependent, which is often also called adaptive. And in that case, it is learned either from my observation matrix X itself or from auxiliary data, so from an additional data set. And I now want to proceed with the examples for both of these. So I'm starting with case number 1. Bilinear decompositions with a data independent basis. And I think you know examples for this already. Talk to your neighbor and make a suggestion. We have 2 minutes time. So for the people who have done signal processing or image processing, this is just things that you know in a different disguise. So I'm thinking of structured data here. So I'm assuming that X, for example, are all short time series. And then one example would be that you want to do low pass filtering. Yeah, yeah, exactly. So let me give us one example. Low pass filtering of time series. So what do I mean by that? I'm assuming that my matrix X is a collection of signals over time. This can be seismographic data, or it could be data from boys, or data from your favorite accelerator, whatever. So you have time series, and you want to get smoothed versions out. Then let's say this would be the original data, and you want to express this approximately in terms of a basis and in terms of coefficients. And one example would be if you simply discard the high frequencies, which is not the best thing to do if you want to do low pass filtering, but you could say that you would use a basis B consisting only of low frequency sinusoids. So that would, depending on which sinusoids you use, this would simply give you the Fourier transform. And if you now use only the low frequency sinusoids, or equivalently, if you set to 0 all the coefficients for the high frequency sinusoids, then you obtain a smoothed approximation to your original data. I'm trying to draw here a smooth version of the original data set. I'm not going into detail here, just want to relate it to things that you might have seen elsewhere. Another example is JPEG compression, which is very important for all of us taking pictures. In this case, the basis B holds the basis functions of the discrete cosine transform. And these discrete cosine transform basis functions, well, these are just cosines. So if I'm trying to draw the matrix B here, the first entry or the first column would be a cosine of frequency 1. And then we would have a cosine of frequency 2. And you get the idea. For this to work, the original signal needs to be mirrored first, but it's a technical detail which I'm ignoring now. So the B is now the basis holding the discrete cosine transform basis functions, and C is also treated. In this case, the coefficients C, they are vector quantized. I will say more about vector quantization in a moment, but for now it means that we don't take the optimum coefficients, but we approximate these coefficients. And overall this gives us a lossy compression algorithm. Lossy meaning you cannot recover the exact image, but it's much, much smaller if you store it in JPEG format. Oh, sorry. Here we go. Filtering, low pass, oh sorry. Low frequency sinusoids. So it's the cosines and sines, some of them multiplied with a complex unit. Yet another example are wavelet transformations or wavelet denoising. One of you mentioned the short-time Fourier transform. This is a more localized variant of the normal Fourier transform. And that is true of wavelets also. So, you know, again, it's not a course on signal processing. We cannot talk about it at great length now. But the Fourier basis is good for signals that look similar to sinusoids, because those are the basis functions. Whereas if you have a signal that consists of a few spikes only, then you need very, very many sinusoids to express that in terms of the Fourier basis. And wavelets allow you to find much more succinct representations for such data. So the basis B for wavelets could, for example, look something like that. So we would have one component that fits data lying here, and we have another component that fits data lying there, and so on. And then, you know, there's a multi-scale hierarchy and many things that we cannot discuss now. Okay, now the basis B holds wavelets, but for denoising, again, the coefficients are manipulated. So the coefficients C are, I'm not sure this is a English word, I will say sparsified. That is, many of them are set to 0. And this setting to 0 can happen in one of two famous ways, namely by hard or soft thresholding. So let's say I'm looking at a single coefficient now. Let's say I'm looking at coefficient ij of my coefficient matrix, and I now want to approximate this with a thresholded version. So I'm just saying f of c of ij, and this would be the identity function, so leaving the coefficient unchanged. And if you now want to have more zeros in your coefficient matrix, there are two natural ways of obtaining that. If you want to, if you want to discard the small coefficients. One approach is so-called hard thresholding, where you say if the absolute value is smaller than some number tau that you set, then the coefficients are exactly 0. And otherwise, you take the unmodified original value. So if the absolute value is smaller than tau, you set the new coefficient exactly to 0. And if it has values larger than tau, you use the original value again. And here at these positions, we have a jump. As an alternative, there is the soft thresholding. I'm using the same axis here. Where you make all coefficients a little bit smaller and set to 0 those that are originally already smaller than some value tau. So in other words, your transfer function for coefficients then looks like this. Okay, so you subtract from all coefficients a constant amount. And set to 0 those coefficients that were already small originally. So there you go. That's wavelet denoising, and that's a very useful method, both for images and for music also. Okay, and MPEG, or the let's say the MP3 format, that would be something similar to like the JPEG system, but for time series rather than images. So I've given examples for this case number 1, where the basis is already known. And I now want to the setting number 2. Namely, that's our main topic for today, the bilinear decompositions where an adaptive basis is used. So in the Fourier transform, in the discrete cosine transform, and the wavelet transform that we just discussed, the Fourier transform basis functions, they have been known for 200 years, and they're always the same, irrespective of whether you are trying to compress a song from Handel or from, well, let's say, song from Madonna, or concerto from Handel. Now I want to talk about systems or bilinear decompositions where the basis does depend on the data. And well, PCA is obviously one example, but I want to start with a different one here. I want to start with vector quantization. Which is very important for telecommunications. So scalar quantization means that you simply, if you have a single real number and you want to approximate it, then you don't give the original real number, but you just transfer the index of a so-called code vector, so of some representative number that in the transmission needs to represent all samples that were assigned to it. A vector quantization is the same thing, but in a multivariate regime. So I'm writing down the objective function. I have my original observations x, and I want to approximate them with the coefficients expressed in some basis. I'm using the squared Frobenius norm as a similarity measure. I want to minimize over b and c. And now I need to, if I just write it down like that, this doesn't specify any particular method at all. So I need to give additional conditions. And one of them is the following. I want to specify the number of code vectors. So I can say that the rank of my matrix B should be no larger than some value R. And this value R is given by the user. And it can be larger or smaller than the dimensionality. So what you do in vector quantization is the following. Let's say you have some distribution in a multivariate, in this case in a two-dimensional feature space, and you want to approximate the samples that you draw from this distribution with code vectors. And code vectors are simply representative points that partition space amongst themselves. So I'm trying to draw this partitioning correctly here. Something like that. And by the way, this is called a Voronoi tessellation of the space. It simply means I assign, if you remember from the k-nearest neighbor classifier, I simply assign each point in feature space to its closest code vector, except that this time the code vectors are not labeled. They are just representatives for the exact observations. And if I now sample from this distribution, I don't transmit, let's say, I don't transmit the two real values that I need. So normally I would need to transmit a feature number 1 and a feature number 2 for, let's say, for this observation here. And now in this compression scheme, I don't transmit the exact numbers, but I simply transmit the index of the closest code vector. Now this, for the system to work well, these code vectors, of course, should be well distributed sensibly. So in high density areas, you want the code vectors to be close to each other. In low density areas, you can afford them to be spaced further apart. and formulate it as an optimization problem, I can write it like that. So I want, for a large collection of observations, this is a finite set of observations, for this large finite set of observations, I want this approximation to be as good as possible, subject to the following constraints. I want some certain maximum number of code vectors. In this case, I used 5 code vectors. And I want each point to be assigned to a single code vector only. So C can only be 0 or 1. And each point must be assigned to a single code vector. So I can write that by saying that my vector of 1s, if I multiply my 1 by R vector of 1s with my coefficient matrix, which has dimensions R by n, I want to obtain a 1 of dimension n. No, something wrong. 1 by n. So what this says is that each observation represented by the coefficients is assigned to a single cluster center. And then to have a bit of terminology, the collection B of all code vectors or of all basis functions is called the code book, which you need to decipher the message on the other end of the line. So in this example, I could number these code vectors. I would represent each point from this two-dimensional space, each point from this R2, I would approximate by giving only the index of the closest code vector. So I would transmit across my line messages, 1, 3, 1, 4, 2, 1, 5, etc. And to make sense of these messages, the receiver needs to know this code book of code vectors. This is the interpretation of C. These are the positions of the code vectors in the full feature space. And C, on the other hand, if you think of it as a clustering algorithm, then these are hard cluster memberships. So each column in C has just a single one, which is a different representation of these indices. It's a binary representation of these indices. Now I've only given this objective function. I've not said how to optimize this at all. The optimization is usually via an algorithm that's called k-means, which we will talk about in a few weeks. And k-means, by the way, will only find a local minimum to this problem here. So the unfortunately, this is a non-convex optimization problem if we optimize over both B and C. No, I didn't want to show anything. Thanks. Go ahead. Yes? Oh, tessellation is just a partitioning of space into non-overlapping regions. Oh, the German word Kachelung. Thanks. I wouldn't have known. So what it does overall is that it approximates each and every observation by its cluster center, where its cluster is simply determined by proximity. Because if you look at the objective function, if you assigned it to a cluster center that lies further away, you would simply get a higher error, which you don't want. Okay, yeah, I didn't say what soft or fuzzy clusters are. This is one example of a clustering algorithm where we have cluster centers and we assign observations to clusters. Hard here means that an observation belongs to exactly one cluster only. The opposite of this is so-called fuzzy clustering schemes, where an observation can be said to belong to two different clusters to some extent, or to more clusters to some extent at the same time. Yes, in this method you partition feature space, so the membership regions, if I can think of this as membership functions, the membership function of, let's say, this cluster center is 1 within this area that you see here and is exactly 0 outside. But there are clustering algorithms where each cluster center is associated with a softly decaying membership function. And these fuzzy clusterings also make sense in some contexts. Oh, okay. So the red points were the cluster centers, and now I didn't want to make this plot too messy, but these probability density function of the underlying distribution, I plotted it, but it's not known in practice. All you have is this finite sample, so these blue scattered points. Okay, you I can go ahead and say you get it by solving this equation. Now, in practice, it's done via the so-called k-means algorithm, which I wanted to talk about only in a few weeks. But what you do is you you randomly initialize your cluster centers, you estimate class memberships, you iteratively move each cluster center to the center of mass of its observations, and repeat until convergence. Okay. But what you see overall is that it's a problem that if I talk about it in terms of here these code books and code vectors and so on, it looks quite different from PCA. But if you look at the formula, it's not so different. So this part is the same. That part is the same. What changed was that we imposed that the coefficients can either be 0 or 1, and that only for a single observation, only one of the coefficients can be switched on. So it's a small change in the formula, but a big change in what the algorithm means, what it does, and so on. So this is a binary decomposition that does something totally different. I will rewrite PCA so you can relax for a minute and to bring out the similarity with the method I want to show afterwards, if I have enough ink. Different letters now to be consistent with bases and coefficients, but it's the same thing that we did before. I want to minimize that over B and C, subject to the following constraints: that the rank of B should be at most R, which is again user specified, and this time R must be no larger than P or N. And secondly, I want each of the basis vectors to have unit norm. And these constraints only, without any additional input of mine. If I now solve this problem, I get out the orthogonal bases and all that. So the orthogonality of the optimal basis. Optimal basis, which we've also known as the principal components. Yeah, these are the small b's are the columns. It ensues, so it just follows by solving this optimization problem. I didn't have to put that in as one of the assumptions. Okay, so this is the same thing that we've discussed most of today, just with different letters. So optimal basis B of principal components, and we get the scaled coefficient matrix C. So C are our, in the PCA we called them the scores. Okay, and now I make a small change to this equation, and we again get something with a totally different behavior. And this is where this orthogonal matching pursuit comes in. I should give you the name first. This is dictionary learning. So I again minimize over B and C. Such that the rank of B must be at most R, which is again user specified, but this time R can be greater than P. Or can even be larger than N. If we have learned, not if I want to learn it here, can be larger than P, okay. Then I request that the individual columns of my basis have length at most 1. Oh, and that? Oof. Computer fell asleep. That's a bad sign. Okay. Oh, okay. And now comes, so this looks very much like we had above for the PCA. And now comes the crucial difference, namely that I want the L1 norm of the L1 norm of the coefficients to be less than some number. Now that looks funny. So first, what do I mean by L1 norm? This is simply the sorry. This is a scribble. It means sorry, delete error of mine. Excuse me. So the L1 norm means that's the sum of the absolute values of the matrix entries. Now, something I start out with something that's easier to understand, or maybe more intuitive. This thing is used as a proxy for the following pseudonorm. Let's say kappa tilde. So if I used this thing here, I would say that I give an upper limit on the number of non-zero coefficients in my coefficient matrix. Unfortunately, this gives, if I request that gives me an NP-hard optimization problem. So you can only practically do this for a very small data set. Because this is so hard, people use the most similar formulation that is already convex, which is this one here. So that taken together is a convex optimization problem. And it turns out that this convex problem is actually a very good proxy for that. So people doing theory on this, they call this miracle the oracle property. And then there are long proofs that under certain conditions this will give you the same set of non-zero coefficients as the real thing. So this is one of the lucky incidents in nature or in mathematical nature that this is true. The zero norm would be, or pseudo norm would be the sum of the number of non-zero coefficients. The number of them, yeah? Yeah, C can have negative entries. Okay, and this gives a method which is called dictionary learning that has been very heavily investigated over the last few years. And I mean few. So, you know, the first papers are always from a long time ago, but actually in the last 5-6 years, many important results have been established and usable code published. Here are, so you see the slide credit is Francis Bach, Julien Maral, Jean Pons, Guillermo Sapiro. You can read it at the bottom. They show here for a very large collection of natural images. So people were taking pictures of people and of forests and of streets and of houses and were estimating a basis B for all these data sets according to a variety of methods here. We have discussed PCA today, and indeed if you do PCA on a collection of natural patches, you get filters that look like this. So it starts like you know, low pass filters, or here that looks like a derivative filter, and it ends up, these things have a higher and higher spatial frequency, ends up with something like that. If you use non-negative matrix factorization, which is very similar to PLSA, you get differently looking patches, and the difference will be more striking if we use faces rather than natural patches to derive all of these. And finally, here are the basis functions that are learned with dictionary learning. So if you restrain, note that here there was no constraint on the dictionary or on the matrix B itself. The coefficient was only, the restriction was only in the coefficients. And yet the dictionary itself starts to look very different, as you see here. And well, what it does, this method, is that it tries to decompose natural images into a collection of bars and line edges and step edges. Okay. Now this is the same for faces. On the very left, you see the principal components extracted from a database of faces. In the middle, you see the components extracted using non-negative matrix factorization, and the authors stressed that on average these are much more spatially localized, even though this was not put in as a restraint or as prior knowledge. And here are the things, the basis functions learned from dictionary learning. And well, the question is, did these people, how big is this extended Yale database? I don't know how many faces it has. So if you go to a very, very large collection of faces, you would probably find things like, individual parts of faces, like you would find only mustaches and so on. Now here are some of the uses. It is actually very successful for image denoising. So you have here a noisy image to the left. Again, this is now from a presentation by Julien Maral. You have a noisy image to the left, and then this image was used to both estimate the dictionary, and this dictionary presumably had black patches only to explain, this part of the code. It presumably had gray patches only to explain these homogeneous areas, and then it had some more interesting patches that, for instance, would try to account for these stripes in the feathers over there. And on the right-hand side, you see the result. If you now use this dictionary with coefficients, only few of which are allowed to have large values. So here, this L1 regularization was used. And you see there's actually a pretty nice denoising. Go ahead. How large are the patches? They are, I think people use 8 by 8, 16 by 16. Yeah, exactly. So in this dictionary learning example, all of the patches in the image were used as columns in the matrix X. And then I'm not sure how large the dictionary that came out was, how large the dictionary in this case was. I have another example from the same presentation by Julien Maral. This is the original, and then it looks, some people would say, prettier like that. And okay, here is an example. This is by Michael Elad, who specifies the size of the dictionary. So this is also a very famous example image for denoising. This is the original. This is the noisy version, which now, given the low resolution of the camera, already looks somehow pretty good, but it's smoothed. And there is the denoised image. And here you find the dictionary that was learned. And in particular, these stripes are very prominent, because if you look at this image in sufficiently high resolution, you will see that it has lots of stripes here, and then there are these checkers in the tablecloth and so on. So actually, it looks like most of the dictionary tries to do justice to the stripes, and things like the face, you can apparently express it with really few basis functions or atoms. So it's, the math is the same, but it's a different community, so they call this dictionary and not basis functions. And what in the principal component analysis was called a principal component is now called an atom, one of these elements of the dictionary. All right, questions? Can we go back to the slide, please? So in the language of this area of research, this is now called the dictionary. So as comments, we have had you don't need to write this down, but we have had a great surge in both theory and applications in recent years. Important applications for this are, for example, denoising, or so-called in-painting which means part of the image has been corrupted or occluded or artificially, people have printed across an image, and you try to estimate the missing parts. And, well, it's pretty elegant, I would say. You see, it's just, 3 lines that specify the whole thing. Considering how good it is in denoising, this is a very simple and elegant formulation. But how do you do it in practice? You probably use one of the existing libraries, and one that's very popular these days is SPAMS, written by Julien Maral and his colleagues. And actually the optimization for this problem, if you use the L1 norm, can be done pretty efficiently. This is what this library does. And this is where the OMP that you mentioned is used. All right. By the way, if you're already given a dictionary, so let's say you want to work with natural images and somebody has already performed this optimization, and you now simply want to use the existing dictionary, then, well, you minimize only over the coefficients. B is given, and then this thing is called not dictionary learning but sparse coding. So if B is given, then the whole method is called sparse coding. Okay, and because we're almost out of time, I will only mention by names more methods that can be written as bilinear decompositions, namely independent component analysis, which capitalizes on the independence or assumed independence of the original signals. And what it does is that it tries to explain your original data in terms of independent signals and the so-called mixing matrix. And the typical example where people motivate the use of ICA is the following. Let's say you have a cocktail party full of people, some of which are diplomats, and you absolutely want to hear what they are saying, and you have a couple of microphones distributed in the room. Now each of the microphones is picking up a mixture of the original utterances, simply because the sensitivity of each microphone is not perfectly localized. So your measurements, your multiple microphone recordings, are linear combinations of the original signals, where each microphone uses a different linear combination coefficients. And you now put in the assumption that the original signals were indeed independent. So you're given X, you're given this assumption, and then you try and estimate both the independent signals and this mixing matrix. And also, just in words, or I just want to mention it here, another technique that can be written in terms of bilinear decomposition is factor analysis, which goes, well, it's a probabilistic method that allows you to put in a bit more prior knowledge than PCA. Let's summarize it as that. Okay, now what have we gained from all this? I simply wanted to put things into perspective. So we have this very large number of methods that do quite different things. We had the dictionary learning, we had PCA, we had here the vector quantization. And they all result, if you look at the equations again, uh, they are all simply bilinear decompositions. They only differ in terms of the precise objective function that you specify. I have not talked about how you actually solve for these things, how you actually optimize these objective functions. But I like this summary because it brings together quite independent threads of research. So amongst the ones that I've shown here, PCA is the oldest. It's been around for close to 100 years. Vector quantization was studied intensely in the 60s, where it started to be used for telecommunication, so to compress signals for telecommunication. And then ICA came, let's say, in the 90s. Again, earlier works, so there were certain pioneering works, but overall they started to take off only in the 90s. And dictionary learning is really quite a young and vibrant subject. And all of these are simply bilinear decompositions, so different ways of analyzing your data in an unsupervised fashion by decomposing it into something that can be called a basis and something else that can be called coefficients. So, what have we done today? We have talked about PCA and an SVD as a linear algebra technique and how it relates to PCA. And that, the big picture, I have not talked about. There are more entries here, so I couldn't talk about, for lack of time, about probabilistic, latent, semantic analysis, or the closely related non-negative matrix factorization. I think I will say something about the former when we talk about graphical models at the very end of the semester.